Hi everyone, I'm Tianshu Hao from Institute of Computing Technology, Chinese Academy of Sciences. Today I'll introduce you AI scenario, a scenario-distilling AI benchmarking. Let's take a look at the landscape of modern workloads. The emerging modern workloads include big data workloads, machine learning workloads, and internet services like search engine, social network, and e-commerce. Realistic industrial-scale applications usually contain multiple subsystems, such as online service subsystem and offline analytics subsystem. For each subsystem, there are various modules. Each module serves unique and separate business operations. Within each module, a series of AI and non-AI components are included. In addition, microservice-based architectures have long and complex execution paths, containing the whole process from receiving user requests to feeding back results. A microservice-based architecture contains various AI and non-AI modules and consequently forms long and complicated execution paths. Previous AI benchmarking work provides a few macro or components benchmarks and fails to model an industrial scale application scenario's overall critical path. This figure illustrates the complexity of a modern end-to-end application. Users send requests over HTTP, which first reach a load balancer implemented with Nginx. Once a specific web server is selected, the latter uses a module to talk to the microservices responsible for composing and displaying posts, as well as microservices for advertisements, search engines, then we compare the modern workloads with traditional workloads from the perspectives of code size, deployment scale, and execution path. This slide shows the difference of code size. The code sizes of modern workloads and the traditional workloads vary by several orders of magnitude. For example, the traditional desktop workloads from Spec 2017 benchmark contains 100,000 lines of code such as data compression, image manipulation. The traditional web server workloads like Nginx website contains hundreds of thousands of lines of code, while for modern workloads, the code size usually reaches up to millions of lines of code, since they have complex runtime environment stacks such as TensorFlow and Spark. And this slide shows their differences from the perspective of deployment scale. For modern workloads, they are mainly deployed on a large-scale cluster that contains tens of thousands of nodes. From the perspective of execution paths, modern workloads usually have longer and more complex execution paths than traditional ones. For example, modern internet service providers employ AI to augment their services and adopt a microservice-based architecture. Thus, the permutation of several of dozens of microservices constructs the whole lifecycle and the critical path of industrial applications. Modern workloads contain diverse modules, complex execution paths, massive scale, and a complex hierarchy of data center infrastructure. Modern workloads dwarf the traditional one in terms of code size, deployment scale, and execution paths. Traditional AI benchmarking methodologies almost adopt macro or component benchmarks, and we will see whether they are sufficient. For AI macro benchmarks, there is no accuracy information. However, accuracy is one of the most important metrics for AI. Flops is no longer the only metric. Our experiments show that even mixed precision training technology significantly improve flops. However, it may deteriorate the model quality. Only using micro benchmarks cannot find it and may lead to error-prone conclusions. Thus, macro-benchmark has those shortages: no quality information, impact of data input for different layers, and no single kernel. Another bottleneck for macro-benchmarks is that AI workloads have no single kernel. Through analyzing 17 workloads in AIBench, we find that there are many kernels, so only using one kernel is not enough. Many existing work adopts component benchmarks which provide a task-level AI model implementation, like image classification. However, our experiments also show its potential misleading. For example, we first benchmark with a single component image to text. Through model pruning, we find that the tail latency shortens by 51% and model accuracy decreases 1%, which is acceptable. However, when we put this component into a real scenario and still use the same pruning technology, we find that the tail latency has no improvement while the accuracy decreases, which is unacceptable. They generate inconsistent conclusions, so only using components may lead to error-prone conclusions. We use e-commerce search intelligence to take experiments and found that the overall system latency indicates that of the Intel execution path, including AI and non-AI components. The experiment's results show the overall system tail latency deteriorates dozens or even hundreds of times than a single component. Therefore, benchmarking a single component cannot reflect the overall system's effect. The online inference module needs to load the trained model and conducts the forward computation to obtain the result. Usually, increasing the depth of the neural network model may improve the model accuracy, but the side effect is that a larger model size results in longer inference time. For e-commerce search intelligence, the model accuracy improvement is 1.5%. We replace ResNet 50 with ResNet 152 in the image classifier, while the overall system 99 percentile latency deteriorates by 9.7 times. Therefore, benchmarking a single component cannot reflect the trade-off between model accuracy and QoS. Someone may argue that we can use the statistical model to predict the overall system performance, but whether a statistical model can predict the overall system tail latency through profiling many components' tail latency performance, our answer is no. We use two state-of-the-art statistical models to estimate the overall system latency and tail latency, a simple queuing model and a sophisticated queuing network model. We find that the gaps between the actual average latency or tail latency and the theoretical ones are large through the experiments using two scenario benchmarks. Our experiments using the state-of-the-art statistical models show that the statistical model cannot predict accurately. There may exist 3 to 9 times performance gap. The main reason for this huge gap is as follows. It is complex and uncertain to execute an end-to-end benchmark, and the service rate doesn't follow the exponential distribution. So the MM1 model is far away from the realistic situation. However, the more generalized model, such as GG1 model, is difficult to be used to calculate the tail latency. Furthermore, if we try to characterize the permutation, so executing dozens of components is an end-to-end benchmark, we need a more sophisticated analytical model such as a queuing network model, which is much infeasible to perform a calculation of tail latency. In conclusion, scenario benchmark is needed. Scenario benchmark is a proxy of a realistic application scenario and a permutation of a series of AI and non-AI components to capture the critical paths and the primary modules. This is the content of our slides. We conclude the reasons why we need scenario benchmarks. Scenario benchmarks reflect the overall system's effects, measure the trade-offs, and collect different level performance data. We propose a scenario-distilling benchmarking methodology. We formalize and distill the real-world application scenarios to undeck permutation of essential AI and non-AI tasks. Then we define the specification and implement the benchmarks. For the scalability and simplicity, we provide a reusing framework to support quickly construction of scenario benchmarks. Through profiling, we identify micro benchmarks. The benchmarks can be deployed on physical machines and simulators. Collaborating with the 17 industry partners whose domains include search engine, e-commerce, social network, and so on, we distill their products or services into 9 representative scenarios: e-commerce search intelligence, online translation intelligence, content-based image retrieval, web searching, facial authentication and payment, newsfeed, live streaming, video services, and online gaming. We distill the scenario stack model into a permutation of essential AI and non-AI tasks and consider it a high-level scenario benchmark specification. To capture the essential parts of the original deck, we propose 6 distinct rules. These rules are our consensus with the industry partners. Though some rules need input from the industry partners, in general, they are generalized, suitable for the other scenarios. Those distinct rules are Rule 1: pruning DAG branches with similar processing logic. Rule 2: pruning the DAG branches with smallest fraction. Rule 3: pruning auxiliary functions. Rule 4: using a state-of-the-art AI model. Rule 5: combining the components occurred in successive steps. Rule 6: removing unnecessary components after performing the above 5 rules. We propose the first reusing framework for easily constructing scenario benchmarks. As shown in this figure, the reusing framework provides loosely coupled modules that are easily configured. It includes the data input, offline training, online inference, non-AI libraries, and deployment to modules. Based on the reusing framework, we can quickly implement a scenario benchmark. The data input modules is responsible for feeding data into the other modules. The offline training and online inference modules are provided to implement a scenario benchmark. The non-AI library module provides non-AI computation and database access. For complex application scenario, the online inference, non-AI libraries, and offline training modules constitute an overall critical path together. The implementation steps of constructing a scenario benchmark are as follows. First, we choose the essential AI and non-AI component benchmarks and corresponding input data from the reusing framework. Next, the permutation of component benchmarks is specified by the scenario benchmark specification. Then, we choose the deployment tools and modify the reusing framework's deployment template. Finally, we train the AI models of the selected AI component benchmarks using the offline training module and transfer the trained models to the online inference module. Based on the reusing framework, we provide 2 scenario benchmarks, including the whole process of e-commerce search intelligence and online translation intelligence. They include query generators, online service, offline training, and data input modules. In e-commerce search intelligence, the query generator simulates concurrent users and sends query requests. The online module is responsible for personalized searching and recommendations, and the offline module is the training stage to generate a learning model, and the data storage module stores data. In online translation intelligence, the query generator simulates concurrent users and sends either a text, an image, or audio to online server. The configuration information is the same as that of e-commerce intelligence. Audio converter receives an audio query and regularizes the text information with the audio. It first converts input audio into a WAV format and reuses speech regulation component. Text translator performs translation and reuses the text-to-text translation components. The offline analyzer performs job scheduling, which is similar to that of e-commerce intelligence, except that they use different AI component benchmarks and update intervals. Our methodology provides a 2-level mechanism to verify whether a scenario benchmark can represent the real-world application scenario. On the specification level, it is much easier to validate whether the scenario benchmark specification captures the essential parts of a scenario, as we can easily reach a consensus about the efficiency of the distilling rules with the industry partners' feedback. On the implementation level, we compare the scenario benchmark with the real-world scenario from the perspectives of both overall system performance and single component performance. From the overall system performance perspective, we compare the overall system latency of the whole execution path and the same deployment. We define their deviation as the ratio of absolute latency difference between a scenario benchmark and a real-world one to the value of the real-world one. The lower the deviation, the closer the benchmark to reality. Next, I'll introduce our experimental results. In our experiments, the online server of e-commerce intelligence and translation intelligence is deployed on a 15-node CPU cluster and a 5-node CPU cluster respectively. We deploy their offline trainers on GPUs. This experiment demonstrates how to drill down from a scenario benchmark into individual modules or even primary components for latency breakdown, explains why a statistical model cannot predict the overall system tail latency, explores the factors impacting service quality, and characterizes the microarchitectural behaviors. The overall system latency indicates that of the Intel execution paths, including AI and non-AI components. Our experiments show the overall system tail latency deteriorates dozens or even hundreds of times than a single component. The gap is 2.2 times 180 times over text classification or recommendation respectively. When we evaluate a new AI model or accelerator using text classification, suppose it significantly reduces the component tail latency. However, it still contributes little to the overall system tail latency. We also analyze the execution time ratio of the AI components with non-AI components of the overall system latency. If we exclude the communication latency, the average time spent on the AI and the non-AI components is 137 and 58 milliseconds for e-commerce intelligence, while for translation intelligence, nearly 99% execution time is spent on the AI components. This observation indicates that the AI components' contributions to the overall system performance vary from different scenarios. Reproducibility is of great significance for benchmark. We repeat two scenario benchmarks 5 times to verify their reproducibility. We use the coefficient of variation as the metric, which is the standard deviation ratio to the mean value. The experiments show that our scenario benchmarks have extremely low variance. We ran the recommendation component both within e-commerce intelligence and real-world scenarios to compare single components' performance. We choose recommendation as it is the most time-consuming component and impacts overall system latency significantly. The results show from a single component level, our benchmark still reflects its importance on the critical path and reflects similar workload behaviors within the real-world scenario. As our many industry partners witnesses, they have to update the AI models in a real-time manner using an AI model for an online service. For example, one e-commerce giant demands that the AI models are updated every 1 hour, and the updated model will bring in the award of about 3% click-through rate and millions of profits. It is essential to balance the trade-offs among model update intervals, accuracy improvements, and training overheads using offline training. Updating AI models in a real-time manner is a significant industrial concern in many scenarios. We evaluate how to balance the trade-offs among model update intervals, training overheads, and accuracy improvements using AI offline trainer of e-commerce intelligence. We resize the input data volume to investigate how to balance trade-offs among model update intervals, training overheads, and accuracy improvements. For image classifier, 51% additional training time brings 4.96% accuracy improvement, and 35% additional training time brings 1.9% accuracy improvement. For ranker, 70% additional training time brings 1.36 accuracy improvement, and 17 extra training time brings 0.12% accuracy improvement. And for different AI components, the trade-offs have subtle differences.
Next section is the conclusion of the overall presentation.
This presentation introduces that AIBench scenario is needed for overall system performance. We introduce a scenario-distilling benchmarking methodology and a reusing framework and two scenario benchmarks: e-commerce search intelligence and online translation intelligence. And this page shows our paper, website, and download link. Thank you for your listening.